Okay, on my side, so you've mentioned this connection with acoustic Mie-resonators. So your Mie-resonator looks a little bit complicated, you know, what you have shown, but I suppose that already, you know, if you have a pillar, a soft pillar on a substrate, this soft pillar essentially will resonate just like a Mie-resonator. I mean, you know.
I don't know. That's not my work. Just follow the papers. People who actually doing acoustic scattering can look at that. It's just what I notice in literature, and because of my okay, I'm not sharing screen anymore, right? So okay, yeah,
but in fact, Yuri, I believe that some very simple geometries, you know, just a soft homogeneous object is already a Mie-resonator. I mean,
you mean acoustic?
Yeah.
Okay, that was my idea. So you should try to look at that more carefully. But of course, it should depending on a ratio between wavelength and the type of modes.
Of course, that's
longitudinal
right.
On transverse, what kind of materials you use and how. But still, there is kind of similarity in that effect. If you
because you know,
my hope,
my understanding is that your resonators are sometimes based on very large contrast with the refractive index. So you have high contrast. And we can easily achieve this in acoustics, for instance. You know, we can have very soft inclusions or very stiff inclusions. So,
no, but as you see, there are only a few groups who are doing that, and I learned about this previous group from papers which was published by my colleagues from Itmo University about acoustics.
It's a great work, and
think about that. I will be very happy, and that's probably interesting direction. But in electromagnetic theory, that's a way to actually reduce reflections and localize energy in open resonators, which probably much easier to do in acoustic by different other means.
So in fact, you have mentioned the work of Capasso. And so in terms of, you know, just very briefly, since, people like Capasso, like Philippe Lalanne and others introduced these kinds of metasurfaces, what are the biggest achievements in your opinion? I mean, what really has driven this field to what it is today? So what were the major achievements in the past, let's say, 20 years? If you would have to give just a list of 5, you know.
No, as I showed at that diagram, there are different communities which actually even do not interact. For example, like in the metamaterials, you have a community working on acoustic metamaterials, and only at the Meta Congress, I think, we start to see each other in parallel sessions, you know, but usually we somehow do not interact. As you understand, people working on metasurfaces, we hardly know about seismic wave protection or whatever screening which people do in Marseille, and all these achievements hardly noticed by them. So these communities are different, and we are driven by different ideas. What is really interesting in terms of achievements? First of all, when Capasso introduced that metasurfaces, many people started to say, "Wow, this is diffraction gratings, nothing new." No, as you probably may expect, every new discovery is based on something previously known and also bring some new concept and new ideas. But I believe that the initial idea, similar to metamaterials, initial idea was negative index. Who cares now about negative index? No, because this negative index can be achieved with periodic media, you know, negative reflection, for example. And but metamaterials evolved into a completely different direction, and people looking for different things. The same with this Mie-resonances. Initially, we will consider it like kind of low loss realization of concept of metamaterials. But now you see with this resonances, interferences, it's completely different field, because similar to plasmonics, when we look at hotspots, hotspots will define your energy localization, will define your SERS and enhancement, whatever. But here you see this interference is a very important tool to actually achieve unidirectional scattering, energy localization, or even nonlinear effect enhancement. It's also different type of physics which associated with that. So we understand deeper what's happening behind that, and looking at the consequences. It's very hard to say that there is only one topic which people should follow, but that combination which I mentioned, hybrid materials, combination with two-dimensional materials, that's amazing direction, because these two-dimensional materials, they're very thin, and some of the properties like transmission reflection is extremely suppressed because they are very thin. Then, of course, they can support exciton resonances and becomes active. But combining metasurface may actually provide not even background, but like important components to actually play with properties of two-dimensional materials, and actually even support them. I mean, physically, place on them and enhance different properties. So it's growing very broadly now in different directions, and it's not just shaping around specific one topic. For me, the whole excitement was to realize that it's a very interesting system which still discover new interesting features. For example, like 2 years ago, we did not put much attention to chiral effect, and now it looks like it's a very interesting direction too. And chirality can be also controlled with dielectric structures, which specifically design specific resonances. I see question in the chat.
So interesting talk, thanks for sharing. Could you please also comment on the possible advantages of plasmonic nanostructures or metasurfaces instead of dielectric based nanostructures? So
good question, smart guy. Now what we are lacking here, of course, we can't get this strong field localization in dielectrics. Our colleagues, Nicolas Bonneau, he tried to actually make a parallel between plasmonics and dielectric structures, and then found some similarities, but still to have this extremely well pronounced, you need the dielectrics with extremely high value of epsilon, which is almost impossible to get. But what is important, that people in plasmonics, we were talking for many years about these dark modes, we were talking about this, what we call collective lattice resonances. But if you talk about collective lattice resonances, this is similar to Fano, it's very broad, But if among these collective lattice resonances, you find some of them who are linked to bound state in a continuum, this will provide you with a tool to enhance Q. And I know that some groups, in particular from Canada, they already demonstrated Q factor 100 for plasmonic metasurfaces, which you understand already a big deal. But if you combine this high Q factor with strong energy localization, that gives you a lot of advantages, because in dielectrics sometimes you can't achieve that. So I think the future is to rethink what you can do with plasmonics, because if look, this bound state in a continuum, it's a kind of mathematical abstraction, so which never achieved in life, because you need infinite system, this Q factor infinity. We understand that it never happens, but it's showing you physical mechanism how to approach that. And if you play with parameters, you know that if you achieve 50 and you're in the right directions, you improve something, you suppress losses of your fabricated structure, and you know that here with that structure you can achieve 500. And you know, that's depending on the design and deeper physical understanding, I think we can bring some new concept in plasmonics. So in terms of advantage, it's hard to say. It's each system works for different purposes. For example, we never try to show similar table as I showed for transmission for reflection, because as you understand, plasmonic doing extremely well for reflection. It's hardly beaten by dielectrics because it's designed for reflection, like mirrors and everything, you know. But it's depend on the functionality which you want to consider. Yeah. But again, this recent developments can pump new knowledge in plasmonics as well for this bound state in the continuum, because it does not depend metal or dielectric. This effect is sensitive to losses, and that's why peaks are not very well observed or very well pronounced in plasmonics. But the mechanism is such that you can actually enhance quality factors in such structures through manipulation. I don't see any other questions.
Actually, Luis Perez is asking a question. Can you come? Yeah, please do, Luis.
Can I ask?
Yeah, sure.
Well, thank you, Professor Yuri, for this fantastic talk. My question is quite simple, and I'm sorry, but because it's only regarding one of the last examples that Professor Yuri has shown us, is in the case of this structure that has a total scattering equivalent for both propagation directions. In that kind of structure, you only have the dipolar, the electric dipole and the magnetic dipole, or do you have any high order?
Yeah, sure. Good question. Of course, people try different combinations, and it depends on different combination. You may, I don't have slide with that, but I can mention that basically what you may do, you may even consider more than two multipoles. You can consider 4 multipoles. And if you consider, for example, dipoles and quadrupoles, you can employ interference to send your radiation transversally. So you come to metasurface normal propagation. Of course, you have some very weak transmission, but majority of radiation goes transversally to your propagation direction. So it's a lot of opportunities. I can send you some references, papers, if you are interested. So send me email and I will send you back. So people thought about that. I mean, there are many open questions, but these are very simple to try answering immediately. So field is already for some time and people try to do it. Yeah.
Thank you.
Thank you very much, Luis. Any other question? It's a unique opportunity to speak with Yuri. Huh? So please use this opportunity to ask any kind of question you have.
So if they can send me emails, I'm happy with emails to answer if they just get it later. Yeah.
And like Yuri mentioned in his last slide, he's also very happy to engage into new collaborative work.
Yeah, sure. I'm always open for any work and ideas because people come from different areas. Mm-hmm. And I know from my experience, you come to different area, you immediately bring some new ideas, which people who are working on a set of problems, they just, I can't say blind, but just we did not even thought about that opportunity. So that's why we need seminars and talking to people. And that's why I appreciate what you're doing, mixing people from different fields, you know.
See, I mean, what you have shown obviously is really exciting because we also work on this beak in acoustics. I mean, I'll get back to you regarding this. I mean, this is really fantastic. This area, I totally agree.
Yeah, I think it's not much done. It's an area when you can expect new results. And actually, you know that experiments in optics, particularly of subwavelength, nanophotonics, are quite hard. And in acoustic, I expect that it can be probably set much easier. Yeah, my former postdoc David Powell, who moved now to different university, he's initiated some work with us and then moved his equipment. They now keep publishing some interesting papers there in acoustic metamaterials.
Oh, very good to hear that. Okay, so any other questions? Sorry to insist upon this, but I mean, since you are really the world expert, in this area, I mean, what kind of invention in this area of metasurfaces is a big wow? I mean, what would deserve, the big prize in your opinion? No, but come on. What would be the one? What would be the one?
No, it's hard to say because there are still it's not the area which saturates. It's really area which rapidly developing. And okay. For example, what was 2 years ago, it's already completely different. People are moving ahead, so it's no sign of saturation. But of course, people like Federico, of course, they consider some options with Nobel Prizes. But I don't know. I know that particular me, I nominated twice. I nominated people because, you can't nominate yourself. You should be requested by Nobel Committee. And I nominated twice this team for metamaterials twice, and then for metasurfaces once. For metamaterials, national combination was, of course, Sajid John and Jablonovich, and of course Philip Russell, because that's something what was introduced in practice. But once I even heard a rumor that we were very close, but all these hypes and that gender effect, obviously very important now.
Okay. Yes. And okay, so now, do you think that it's a very good direction, this kind of space-time modulated metasurfaces? Do you think that in optics it's doable, really, to
it's hard, but it's doable. And it is really nice that people discover extra dimension, extra opportunities, and particular time is unidirectional. It's kind of change your mind and push you to think about different physics. And no, it's really nice, but I do not see something absolutely fascinating in terms of realization, application, how it can be done, but maybe I'm wrong. Similar things with the topological photonics. It's nice. It's a very nice toy. With interesting physics involved because people were working on photonic crystals for many years, but we didn't realize any topological properties and did not actually look how they combine. So that's very nice. But in terms of applications, I think the worst thing is that people trying to oversell, as you know, photonic crystals as well. It's some kind of overhype, oversell, and that's actually produce opposite effects. So people, because when you compare with solid state physics, you can really have a unidirectional scattering, but in photonics, if you play with different polarization, it will be backscattering. So it's kind of complicated realization, but some interesting features, of course, can be demonstrated and achieved, and it's good that people looking at that.
Okay, fascinating. So I would like to thank you again, Yuri, for this amazing talk and for giving us the opportunity to ask you some questions. And next week, we will welcome Erik Hiltunen from the mathematics department at Yale University. So it will be switching from photonics to pure mathematics next week.
Okay, Sebastian, I will try to subscribe and to stay in touch. Because your program works very well, sending reminders, and this platform And thanks for inviting me. Okay.
Yeah, and we will certainly get in touch because, yeah, I mean,
okay.
I definitely read your work, so I'm among the people who.
Okay. Thank you very much, and hope we all will meet somehow in real life, because I just came from Clio, and it's a completely different impression when you have people in person, you know, because talks are not very important. Some investigation I recently heard that actually talks at the conference we just only make 15 or 20% of all activities. The rest comes from all this networking, meeting people, talking, just even seeing faces of people which you saw on the paper, like surnames, and make a completely different. It's just feel your activity with human life, human being component, you know.
I totally agree. Yeah, this is so, I mean, we need the social experience. I mean,
yeah. Okay. Thank you very much, and good luck to your seminar series. Yeah.
Okay. Thank you very much, Yuri. Bye. Bye, guys. Stay safe, all of you.
Bye, all.